formula is the smallest reduced formula. All right, so this will make sense in a sec. You know what? Let's define that something else. No, we'll say this: smallest reduced. So it gives you the ratio of atoms in the molecule. So for example, all right, C6H12O6, that is glucose. Okay. That's the molecular formula. The molecular formula tells you how many of each atom are in the molecule, the actual molecule. The empirical formula tells you the ratio of those atoms, i.e., so be like going from 2 over 4 as a fraction. What would you write that in reduced form? It'd be 1 over 2, right? So what can I divide 6, 12, and 6 by? 6. You can divide them all by 6, right? Which would give you CH2O. This is the empirical. This is the molecular. Okay, so the empirical gives you the ratio of the atoms in reduced form, essentially. The molecular gives you the actual number of atoms in the molecule. Okay. So the relationship between a molecular and the empirical is the molecular formula is equal to N times the empirical. You're just multiplying. So if I'm going from the empirical to the molecular, in this case for glucose, I'm multiplying everything by 6. That N is always a whole number. So it's 1, 2, 3, whatever. I want to learn how to calculate that. We'll do a lab where you get a compound and you have to figure out the empirical and then the molecular formula of the compound. Okay.
In math, the funky number for all, the funky letter for all integers is
0. Yeah. So for glucose, N would be 6 because we're multiplying everything by 6. Okay, so we're going to practice where you get the ratios and stuff, and then we're going to start to build up to getting just masses and converting them. One more example. If I have CH2, C2H4, C3H6, I mean, you can go all the way up, C100H200, not 2,200. These are all different compounds, okay? But they have the same empirical formula. What's the empirical formula here? CH2, right? And the empirical formula is CH2 because I can reduce all those down to CH2. Okay. But they are actually different compounds with different properties. Right? So empirical formula just tells you the ratio of the atoms in the molecule. That's all it tells you. So this is going to be the opposite of what we just did. Percent composition is going this way. Empirical formula is going back the other way. It's kind of essentially. All right. We are going to have to convert decimals into whole numbers. So there's a bit of math here, but there's some common ones. All right. If I want to convert a number that ends in 0.5 into a whole number, what do I multiply by? The lowest number. You'd be multiplying by 2. 2 times 0.5 is going to give you 1, right? If you see 0.67, 0.33, things like that, those are thirds, multiples of thirds. So you would multiply by 3. And if you see 0.25, that's a quarter. So you're multiplying by a fourth. Essentially, you're taking a fraction and you're multiplying, like, so say 1.25. 1.25 is 5/4. If I want to convert that into a whole number, because you don't want fractional, you don't want C to the C5/4 H2. You can't have 5/4 of carbon. All right, so you want whole numbers. So if you multiply this by 4, you get 5. Okay, that's what we're doing. We're getting rid of the fractional component of this. And if you have like 0.2, 0.4, 0.6, those are fifths. So you're going to multiply by a 5. You'll see when we do this, which we're going to do right now. Okay. Are we ready? Are we excited? You don't seem very excited. I think that Quinn's honest and is just shaking his head. I'm not excited. Okay, here we go. So you've done the percent composition. You found out that your formula is 70% iron and 30% oxygen. We need to go back and figure out the empirical formula. Okay? You always assume, I guess, again, unless otherwise stated, that you have 100 grams because percent is per 100. So it makes things nice and straightforward. Okay? All right. So if I'm assuming we have 100 grams and 70% of it is iron, how many grams of iron do we have? 70 grams of iron. So mass percent by 100 grams. That means if we're doing iron here, we have 70 grams of iron. Basically, you're converting the percentage right into grams. That's why we do it out of 100. How much oxygen do we have? 30. 30 grams. Okay. So now if I said to you, you have 70 grams of iron. We don't want grams. We want everything to be in moles. So if you have 70 grams of iron, how many moles is that? Well, you got to do a conversion. 70.0 grams of iron. What's the molar mass of iron? 55.8. So that means 1 mole of iron is 55.8 grams. So those go away. 70 divided by 55.8 is, now carry at least 3 decimals. The more decimals you carry, the better your answer is going to be. Okay? We're not worried about sig figs. 1.25448. Okay? Carry at least 3. 4 is better, 5 is better. Okay? All right. You got to do the same for oxygen. So we have 30 grams of oxygen. What's a mole of oxygen? How much does oxygen weigh? 16. Perfect. 16.0 grams. 30 divided by 16 gives me 1.875 moles of O. Okay. Okay, this, I don't know why it's here. This should be here. But basically, now, to get the ratio, you divide by the smaller moles. Okay, whatever the smaller number is. So what's smaller, 1.25448 or 1.875? 1.25448. That's the smaller number. So you divide by the smaller number. So we go, okay, 1.25448 divided by 1.25448. You obviously don't need to write that step. What is that going to be? What's any number divided by itself? It's 1. So you have 1. That's the mole ratio. Now you do it for oxygen. You have 1.875. You're dividing by 1.25448. What is that on a calculator? Okay. 1.4946. We're going to round that to 1.5 because you're going to see things don't always, science isn't like perfect. You don't get these perfect numbers all the time, especially when we do this in the lab. You're going to see you're going to have to work with some not the nicest numbers. Okay. So this 1 and the 1.5 are your mole ratios. Essentially what it's saying is you have this. I'm going to write it. You have, I'll just write it right here. This intermediate step, they don't have a thing for it. It's saying you have Fe1 O 1.5. That's the ratio. But we don't want decimals because you can't have 1.5 oxygen atoms. So what can I multiply through here by to make them both whole numbers of the lowest thing? So if you multiply both by 2, right? So this is the times 2, and you get the empirical formula, which is Fe2O3. Okay. So the reason this is important is because we took a percentage, which you can measure. You can measure this stuff, right? In a lab, you can measure the percentages because you can measure grams. You know how much you started with. That's what we're going to do in a lab. And then you can do some calculations to go from percentages to an actual formula. All right, let's try it one more time. Empirical formula of 39% silicon and 61% oxygen. All right, we assume that's out of 100. So what is my grams? So we have silicon, we have oxygen. What's the mass you have? What's the mass of silicon? No, not the molar mass. The mass you have in the sample. It's your percentage, 39 grams, right? Because we're assuming it's out of 100 grams. So we have 39 grams. And we have 61 grams of oxygen. Okay. Then because we don't like mass, we want moles. Now you're going to do your conversion to moles. 39 grams. 1 mole is 28. No, yeah, 28. 28.1. We'll give you moles. 1.3879 moles. And then we have to do it again for oxygen. So a mole of oxygen, 16 grams. So that gives you 3.8125 moles of oxygen. All right. So now you got to get the ratio. So what number do you divide by? Smaller number. Divide by smaller number, which is the 1.3879. So if you divide that by 1.3879 itself, you get 1. You divide this by 1.3879, you get about 2.75. You want to go to like 2 decimal, like on this one, you want to get these numbers to be, one of them is always going to be 1, and the other one you want to 2 decimal places. Okay, so what that means, this is the ratio, right? That means you have, if you wrote it out, if you want to think of it this way, SI1 O 2.75. How do I turn, what am I going to multiply by to turn this into a whole number? 4, right? Because it's ending in 7.5. And if you look back here, you multiply by 4. Okay? So you multiply them both by 4. So if you're going in this one, it's times 4 times 4. You get 4 and you get 11. Is that right? And so therefore, this formula is SI 4 O 11. That's the empirical formula. Now, that's not always the molecular formula. We're going to learn how to do that later on because there's one more wrinkle, but we can do that later. So we ended 5 minutes, don't we? All right. Well, we'll stop there. We'll pick this up whenever.